Hey class, how is it going? So, um, you have seen this interesting question there, right? What does the sunlight contain for engineers, for us? We are engineers. What does the sunlight contain for us? Mm. So, yeah, it should be something more than heat, right? Um, right. So that's the question we will be trying to answer today, and that was the question, very tough question for physicists, and until the late 19th century, people had very um, debated. They debated very well because the idea was very not very intuitive, but still it was very groundbreaking, very radical idea. That's why it took so much of time. So we will see how we can answer, or how people in the physical community they answer that question, and how we can utilize as engineers those concepts, right? Okay, so to answer that question, I want to start with something interesting from Planck's idea. Basically, Planck's idea was he thought the energy, radiation energy, was composed of discrete particles, not particles actually, packets of energy, which he called quanta, or quantum of energy, right? So he thought the radiation, whole radiation, as a gas of photons, right? So photonic gas is the radiation. That's the Planck's idea. And if we move on with that consideration, we actually come up with this distribution function, which you can see this I for irradiance of the black body. And by the way, if you have not heard about black body is a body which actually can absorb and emit any incident radiation on it, right? So ideal black body emits and absorbs every radiation that's falling on it, right? So the irradiance of the black body, which is emitting photons with wavelength lambda and at temperature T, is given by this complex function, right? And because that complex function is there, it is actually hard for our mind, at least for this level, to visualize that easily. And that's why I have I came up with this code in Python. And don't be scared if you have not heard about Python before. It's just a computing platform to simulate, to analyze the data, or to visualize those complex concepts like that. Okay, so I will give you this notebook, Python notebook, and if you are interested, I can teach you the basics of Python as well. All right. Okay, so let's go ahead and plot this irradiance. Excuse me. And this irradiance, which basically is the measurement of brightness of black body, right? Which in other words is the number of photons being emitted per second per unit area, right? So that if you plot the irradiance against wavelength, then you get this nice curve, defined curve. And the good thing about this Python is you can play with other variable, which is temperature here. And if you decrease the temperature in this case, the curve is distributed differently than if you increase the temperature, then the curve is going toward left, right? The peak of the curve is going toward the left, where it belongs to the lesser wavelength, right? So what this means is the energy, as you increase the temperature, the energy goes high but it does not go to infinity, which, by the way, classically, in old concept, people used this famous relation using a theorem or principle called equipartition theorem. And they try to explain the same thing using this concept, but as the temperature went up to infinity, then the energy also went up indefinitely, right? So that was the problem. It was popularly known as ultraviolet catastrophe, right? So that was not actually explaining the behavior of black body at high energy or low wavelengths, right? And so, like you see here, this is the very defined function, and it's very interesting to see that the peak is in one particular wavelength, and that has also different meaning. But at this level, let's not go into that depth. And what is the actual irradiance of the sun if you measure experimentally? So it looks like pretty much same. I pulled this image from Wikipedia, and this red bump, it follows very closely with what we received from the simple mathematical equation given by Planck, right? So it turns out that the solar radiation contains photons, right? Discrete energy packets, right? So those photons are distributed in terms of wavelength or energy, and as you see here, the UV photons are less in number. They might be high in energy but less in number, and visible photons, they are maximum in number and little lesser in energy. And the infrared photons in the right end, they are less in number and less in energy as well. So as engineers, that's important for us. So as engineers, what do we think we need to use? We need to focus on in terms of utilizing the photons. It should be visible photons, right? Because they are maximum number. They come up with maximum number and relatively higher energy, right? So as engineers, our goal should be to develop visible light-driven semiconductors. I'm saying semiconductors because they get excited by particular wavelength, and that has different advantage, meaning which we cannot cover right here. Maybe we can cover later on if I get chance. So the idea in summary is the semiconductor, which you might have learned in your previous classes, physics classes, they are separated. The conduction band and valence band, they are separated by a definite gap in energy. And once the valence band is excited by proper, I'm saying proper, we'll see how and why that proper is important later on. If this material is excited by proper photon, then the electron is excited to higher energy level, which is the conduction band, right? So, it happens in the order of Avogadro's number, Na, because we are dealing with the material. If you think of 1 mole of material, then these electrons are up in the order of, the number of electrons excited are in the order of Avogadro's number. So you are basically, populating the electrons which are negatively charged and leaving behind positively charged holes, right? So basically you are forming negative terminal to simplify the things, and positive terminal like a battery, right? So if you have a battery, then what you can do is, if you complete the circuit, then maybe the electrons will find path to travel, constituting the current, which in this case is photocurrent, because you are using photons or the light to create that current. So maybe you can get photocurrent, and in that case people say photovoltaics, PV, right? And in solar roofs, solar panels, everywhere that concept is utilized, right? And if you know, for some reasons, if your plan is to do something else, like you might want to drive reduction reaction, because you have electrons already with negative charges, you can, you know, reduce some compound material, and you can oxidize possibly, and you know, if you combine this action, reduction and oxidation, then you can say you can you know, drive a redox reaction. And actually in lab, people are constantly looking for splitting water to get hydrogen and oxygen, because hydrogen, if you burn in oxygen, it does not give any pollutant like carbon, so it might be helping like a clean source of energy, right? So just by using water, seawater, abundant water, and, you know, sunlight, it's new, you can create hydrogen and oxygen, and that possibly can replace the limited reservoir of coal and petroleum, you know, energy resources. And that's very huge deal, because they give carbon, but this system does not give, right? So that's an example. And again, this is just a theory. There are so much of you know, hurdles to overcome in terms of chemistry and engineering, and hopefully I will get a chance to cover those interesting things in future with you guys. So for now, that's it. Thank you so much. I hope to see you soon, and I hope to work together. Thank you.